Welcome to the video on proving trigonometric identities. Let's start by addressing what is an identity. Here's an example of an identity. Obviously there's no trigonometry in it, but it's an identity nonetheless. An identity is a mathematical statement, usually an equation, which is true regardless of what value or values you choose for the variables in that statement. For example, what makes this statement an identity is the following. If I were to plug in any number for the x's, say 46, just totally made that up. Because this is an identity, it should be the case that both the left and right side of this equation work out to be exactly the same thing. And if you use the order of operations, you will in fact find out that both the left and the right side are the same. Feel free to pause and check the algebra. The point being, however, that there's nothing special about the number 46. If I had done this for any other number, both sides would have worked out to be the same. They wouldn't have both been 105, but they would have been the same as each other for sure. So an identity, again, is a statement, usually an equation, which is true no matter which value you pick for the variables. Now, before we get into the bulk of this video, it's worth noting that you've seen identities before, like this one, but in a different context. The context that you've probably seen identities is the following. The teacher presents an equation like this, and without telling you it's an identity, asks you to solve for x. And you look at the equation and you think, okay, this is a basic linear equation. I know how to solve for x. And so you go about the business of solving, having no idea that what you're solving is actually an identity. And here's how it would play out in most classes. You would maybe distribute the 2 and the 5, do some further algebraic simplifications, maybe even subtract 2x from both sides, or maybe not. Either which way, you realize quickly, under the guise of, quote, solving for x, you realize that the x's cancel out, leaving you with a true statement, 13 equals 13. Your teacher, professor, has probably indicated back at this point, well, this is an equation that has either infinitely many solutions, maybe one way to say it, or you may be familiar with the phrase all real numbers as the solution. So you've seen identities before, but you've been given identities that you didn't know were identities. You didn't know that both sides of this equation would equal each other regardless of which value you pick for x. So because of the context, you would discover that it was an identity and then say it was true for all real numbers as the, quote, solution to the equation. In trigonometry, we don't hide the fact that what we're giving you is an identity. Here's the most common identity that you're familiar with. You might even know it as the equation of the unit circle, x squared plus y squared equals 1. Or y squared plus x squared equals 1 in the order I've written it here. Nonetheless, this is also a trigonometric identity. Why? Because whatever value I were to plug in for x, I would get both sides of my equation equal to each other. And just to show you one example, I've picked 5 pi over 6 for x. We're not proving this identity. We haven't gotten to the bulk of the video yet. I'm just trying to give you a sense of what a trigonometric identity is. So, I've randomly picked a number for x. It happens to be one of our favorite 16 arc lengths on the unit circle. You may be familiar with 5 pi over 6. I'm going to work this out and show that it's a true statement. By the way, look at the squared above the sine and the cosine. In case you've forgotten, which many do, those squareds are placed there for a reason that I don't fully understand, because what they really mean is to find the sine and cosine of 5 pi over 6 and square your results. I will for the rest of my life be perplexed about why the squared is written there, but it's a tradition that I can't seem to change. Too many people involved in it. So, remembering that the squared above the sine or cosine really means what this bottom line shows here, let's work out this equation. The sine of 5 pi over 6 is a half, and the cosine of 5 pi over 6 is negative radical 3 over 2. This is just basic unit circle stuff. If you're not familiar with it, you can still understand the contents of this video, so don't worry if you're not up to speed on your unit circle. Now, if I square these two fractions, I do end up, and I didn't show the algebra here, but the important point is that if I square these fractions, I get a true statement. 1/4 plus 3/4 is 1. And so I've proved that this equation is true when x equals 5 pi over 6, but it turns out there is absolutely nothing special about 5 pi over 6. This equation is true for literally any value of x, and that is what makes it an identity. Now, this video is about proving identities, and we're not going to prove that here. But we will prove other identities as we go along. This problem was simply presented to give you an example of an identity that you already know and show you that and indicate that it's true for all values of x, and to give you one as an example. So what does proving identities mean in our class? Well, here's an identity that we're going to prove in a minute or two. But before we start, I have to talk about the format of how it is that you go about and prove something. First of all, this statement is true for any value of x. If you were to plug in 5 pi over 6 for all the x's, or 3 pi over 2, or 5 pi, or any number for that matter, it wouldn't even have to be our favorite 16 arc lengths on the unit circle. If you plug your age in for every one of these x's, both sides of the equation would work out to the same. Now, how do we prove that these two things are equal for all x? Should we start plugging in random x's, and each time we do, show that the left side and the right side work out to the same? Absolutely not. If we did that 1,000 times, we wouldn't have proved that it's equal for all x's. We would have only proved that they're equal for the 1,000 x's we chose. And you can't prove something is true for all x's by showing a bunch of examples that it's true for certain x's. So we're not going to have a particular value for x here. Well, if we're not going to, then how are we going to prove that they're equal to each other? Well, we have two options. We can start with the left side of the equation and work it out and show that it equals the right. If you can see the colors here, I'll refer to green and red, green on the left, red on the right. What I can do here is I can start with the left side of the equation, and I can do some manipulation of this expression using algebra and using other identities that I know to be true. And using a combination of algebra and other identities, I have to, through 5, 6, 7, 8, 9, 10 steps, how many ever it is, I have to eventually work that out and show that it equals the right side of the equation. But you don't have to start with the left side and work it out to equal the right. Reversely, you can start with the right side and work it out to equal the left. And if that's my choice, then I'll take the right side and I'll do some algebraic manipulations and other identity substitutions until I eventually get the left side of the equation. So it doesn't matter which side you start with, but you have to pick a side and start with it and show that it equals the other side. And if that seems a little vague, I think it'll make more sense after you see this proved. So, what I'm going to do here is I'm going to start with the left side of the equation. Here's the left side of the equation. By the way, if you're in my class, which there's a high chance you are if you're watching this video, you have to recopy the side of the equation that you're starting with as part of your proof. By my rules, it's considered an invalid proof if you don't literally recopy the side that you're choosing to start with. So that's what I've done. I've rewritten the left side because I've chosen to start with the left side. So what do I do now? Well, you have a lot of options. Now what I did, I looked over about 30 different trigonometric proofs. I realize you haven't even seen one yet. And I compiled a list of the things that you can do to be successful 95% of the time. Probably I should state that better. 95% of the things that you'll ever do in a trigonometric proof are somewhere among these 12 options. That doesn't mean these are your only 12 options. But if you're in a class of mine, you should be pretty safe with this list. If you're not, there are other things you can do. The basic rules are here that you can do any kind of algebra or substitutions you want as long as it's a legitimate change in equality. I'll show you what I mean by that. So the first thing I'm going to do here is I'm going to distribute. Look at the left side of your screen and where we're starting, and notice we can distribute the cosine. So I've distributed the cosine here. You may want to hit pause and convince yourself I've used the distributive property properly. And now that I've distributed the cosine, I'm going to use some replacement rules that fall under the category of converting everything that's not a sine or a cosine into sines and cosines. Well, look at the expression I have now. There's two things that aren't sines and cosines. I have a tangent and I have a cotangent. So I'm going to replace tangent with sine divided by cosine, which it is. And I'm going to replace cotangent, which is the reciprocal of tangent, with cosine over sine, another identity that we already know. Now, at this point, you might be asking yourself, so do I always convert everything into sines and cosines? Absolutely not. I just decided to in this case. And why did I decide that, you might wonder? Well, when you see what's about to happen, you'll see why it was a good choice at least. So what I'm going to do next is I'm going to use an algebra rule. I'm going to cancel. Notice by looking at the bottom expression there that the cosines cancel in the first term because anything divided by itself is 1. And the sines cancel in the second term for the same reason, leaving me with a much simpler expression. And now, it seems logical to me that since I have cosine times cosine, I could rewrite that as cosine squared for simplicity. Well, notice what just happened. I just ended with the side of the equation that I didn't start with. And in the broader sense here, and you may be a little confused as to why I'm choosing certain things at certain moments, but put that aside for just a second and try to get a bigger picture. What have I done here? I picked a side to start with. I did a combination of replacements and algebra, my two main categories of options. And through a process of various replacements and algebra steps, I've magically produced the side of the equation I didn't start with. You may see it in red here. And that's the process of proving a trigonometric identity. You start with one side, do replacements in algebra in any order you choose until you magically create the other side. Now, it would be natural to ask two questions here. How did I know to start with the left side? And how did I know which of my 12 options on the right to use? After all, I made these 3 available to myself while ignoring the other 9. The answer to the first question, how did I know which side to start? Trial and error. And how do I know which options to use? Trial and error. In fact, the thing you're looking at now, this formal trigonometric proof, is the final product of many failures. So when you see a trigonometric proof, you don't know how many bad ideas the prover chose before they presented you with this. Because oftentimes we do algebra or make replacements that lead us down a dead end and we have to start over again. This may be the person's 7th attempt that you're looking at here. Now, being that it was actually me who did this and I've been proving these things for 38 years, it's not likely that this was my 7th attempt. But nonetheless, you as a prover, a new person to the world of proving trigonometric identities, you probably won't have success on your first, second, or third attempt on any given problem. So how do you get from where you may be at this moment, sort of new at the subject, to somebody who gets proofs right on their first try? Well, you probably already thought this. Lots of practice. Unfortunately, proving trigonometric identities is one of these topics in math where there's no formula that you can follow. I've given you a guideline with 12 steps, but fundamentally, it's up to you to try, fail, and ultimately try and succeed. Now, before we go on to our second proof, I mentioned earlier that we can make replacements based on other identities we know. There's a somewhat standard list of identities that are accepted that we can use without proof. These are called the Pythagorean identities, the top one you just saw in a previous problem. There are also the ratio identities, and we used both of these in the previous proof. There are also reciprocal identities, and you probably are in a trigonometry class at this point, and you probably know these already. If not, there they are. Now, these three main categories of identities are not things that will prove. These are identities that we accept without proof, and you can use them in your proofs. In other words, you're going to use identities that were already accepted to prove other identities that you're given to prove. Now, there's a much more extensive list of, quote, accepted identities. So most teachers and professors, and me in particular, will accept any of these as truth without proof, and you can use these to prove other identities, and that's what we're going to see 4 more examples of in this video. Before we go on, a common thought students have when they're presented with this page is, my goodness, do I have to memorize all of these for this course? Well, if you're not in my course, then that would depend on your professor, but if you are, yes, you have to memorize all of these. Students often ask, can I use this on an exam? If you're in my class, then no. There's one main reason for that. The main reason is no human is meant to memorize these long term. I have, after 38 years of using them. But you're not expected to memorize these long term. But here's the idea, and I'm talking specifically to anyone who's in one of my courses now. And actually anyone else as well, when you think about it, if you are forced to memorize this extensive list, you won't remember it long term, but when you need it in a pre-calculus or a calculus course or a differential equations course, you're going to say to yourself, oh, wait a minute, there's a sum or difference identity that I could use here. I don't remember what it is, but I know it exists. And you'll be motivated to go look it up. So by forcing ourselves to memorize the identities, we're not going to remember them 6 months from now, but we're going to remember that they exist. and be able to go use them as references when we need them. All right, with that being said, all right, with all that in mind, let's take a look at another example. Suppose we wanted to prove this. Before we do, I want to remind you what it is that it means to prove something. We're going to prove that no matter what x is, any x you could choose, 731, pi over 2, negative 13, for any x you could choose, that these two quantities always have the same result. They're equivalent expressions. Okay, let's bring back the 12 most common things that you can do while proving. I'm going to start with the left side. Why? I don't know. Just felt like it. All right. First of all, to square something is to multiply it by itself. This is a good moment to remind you that exponents do not distribute into parentheses. So to square this thing, I'm going to have to multiply it by itself. So I'm going to have to use FOIL to multiply that out. Now, I'm going to combine the two terms in the middle. Notice they're like terms. That's not really on my list of 12, but you can do other things that aren't on the list. Remember, this list is just the most common things you'll do, but some of the most basic algebra things I didn't think were worth listing. So combining like terms is kind of obvious there. What I'm going to do next is I'm going to rearrange the terms. So notice I haven't done anything here other than rearrange the order of the terms, which of course you can do in algebra. There's nothing mysterious about that. Of course, the question might be, why would I bother to do that? Well, look at the first two terms now that I've rearranged them. The first two terms are sine squared plus cosine squared. And according to one of our Pythagorean identities, sine squared plus cosine squared of any number always equals 1. Now the next thing I'm going to do is an other replacement. Remember that giant list of identities that we just saw? One of them said that 2 times the sine of x times the cosine of x always had the same value as the sine of 2x. That was on that list. And notice, I've now produced the side of the equation that I didn't start with. So let me point out a few important issues one more time. First of all, a proof must start with either side of the equation you're proving. And through manipulations and replacements and use of algebra, you should produce the other side of the equation that you didn't start with. And again, if you're new to this, you have to be thinking something like the following. Okay, Professor Vasidlo, I understand all of the work that you did, but I would never be able to reproduce this kind of thing on my own. Well, you'll feel that way for a while. You have to go down many wrong paths of trial and error until you start to get a sense for how these proofs work. It's not something that's going to come naturally to you, although it may, and if it does, then you're lucky. But more than likely, you're going to have to really work at this. Try, fail, and eventually try followed by succeed. So here's another identity that we're going to try to prove. I'm going to start with the left side. Now, up until now, I've been saying that it's random which side I start with. And to some extent, that's true, but imagine I were to start with the right side of the equation here instead, just cosine x. There wouldn't be a lot to do, would there? What are you going to do with cosine x? Sometimes I have a tendency to start with the more complicated looking side, just because it gives me some algebra to work with. But again, that's not a rule, that's just me. So the first thing I'm going to do here is I'm going to factor. What made me think of factoring is that I have two terms and there was a secant in each one. That doesn't mean that factoring is necessarily going to be successful, although it did turn out to be. So I factored out a secant and I got this. Then I saw the 1 minus sine squared in parentheses, and I thought, oh, there's a Pythagorean identity. 1 minus sine squared equals cosine squared. That was on that giant list we saw earlier. So I made that replacement. And then I decided to use a reciprocal rule. The secant is 1 over the cosine. I thought that might be handy here because if I had everything in terms of cosines, maybe I could get some simplification going. So next I just used a basic fact of algebra that a fraction times a non-fraction involves multiplying the non-fraction by the numerator only. That's just some basic middle school fraction work. And then I decided to cancel the cosine from the top and bottom, leaving me with cosine. And lo and behold, I have the expression that I wanted to create on that. Here's another example we can look at. We're going to prove this identity right now. I'm going to start with the right side of the equation. This is probably the first time I've started with the right. There really is no rule about it, although there's more to do on the right. If I have a division, I will often opt to start with the fraction side just because it gives me more options on what I can do. But again, there's no rule and only trial and error can teach you any of this. So we're going to start with the right side. Now, I'm going to show you something called the conjugate trick that you may be familiar with in algebra, but haven't seen in a trigonometric context. I'm going to multiply this right side of my equation. I'm going to multiply it by 1. What do I mean by that? Well, look at the fraction I'm multiplying it by. I'm multiplying it by 1 plus sine x over 1 plus sine x. Anything divided by itself is 1, so I'm effectively multiplying this by 1 and therefore not changing its mathematical value. That being said, however, it's important to note that why I've chosen this particular version of 1. After all, I could have multiplied by 17 over 17. That's equal to 1. It wouldn't have done me any good. What I've done here is I've chosen something called the conjugate. The conjugate is the conjugate pair of two-term objects. Are two two-term objects that have opposite middle signs. Notice in the original expression I had a 1 minus sine x, that's 2 terms. If I switch that middle sign to plus, that's called the conjugate. So the two denominators you see at the bottom there, 1 minus sine x and 1 plus sine x, are conjugates of each other, or a conjugate pair, if you will. Now, why on earth would multiplying by this help me in any way? Honestly, I'm not sure I would have ever thought of this myself. You're only hearing this from me because I heard it from someone in 1983. And it's just one of these clever things that a mathematician thought up. All I can do is show you why it works. Okay, so what I'm going to do now is I'm going to multiply these two fractions by multiplying straight across. So I've multiplied across the tops, and that's pretty easy to see what happened in the numerator. The denominator may or may not be obvious to you. Basically, it's FOIL, but a lot of terms canceled. If it's not obvious to you right now what happened in the denominators, hit pause, do FOIL, and you'll see. Okay, now you're about to see why the conjugate trick pays off in some cases. Notice the denominator is 1 minus sine squared x. There is a Pythagorean identity on that giant list of formulas we saw earlier that says I can replace 1 minus sine squared x with cosine squared x. Now, still at this point, you might think, Well, I'm not seeing any progress here. How on earth am I to know to do any of this stuff? Well, the first time I did this proof, in 1983, I probably tried 5 or 6 different routes and got nowhere. Probably went to bed frustrated and had to wake up and try it again, and on the 6th try, I tried this. And that's the nature of proving trigonometric identities. But nonetheless, let's continue. So what I did next was I thought, I'm going to split one fraction into 2. This is essentially the reverse of the common denominator rule. If your denominator is a single term, it's often useful to split it up into 2 fractions, especially given the fact that I'm trying to turn this thing into tangent plus secant. Look at the original problem. Look at the side I didn't start with. That's what I'm trying to turn this whole expression into. So if I'm trying to turn it into a 2-term expression, it would make sense to split it up. And once I did this, I realized, hey, I can cancel some things here. In both of these fractions, a cosine on the top cancels with one of the 2 factors of cosine on the bottom, leaving me with this. If you're a little shaky on your algebra, hit pause and convince yourself that that was a valid cancellation. Now, each of these new terms can be changed into other terms by using the ratio and reciprocal rules, again from that giant list of identities you saw earlier. The 2 changes that were just made are on that list. Now, is this what I wanted it to equal? More or less, but I think for formality's sake, I'll rearrange the terms here so that it matches exactly what I was trying to get it to match all along. This is a pretty tough proof. And here's our last identity that we're going to prove. I'm going to start with the right side here. I think I was motivated by the fact that there's more to do over there. The other thing that motivated me as well is that those 2 expressions you see on the right side here, there's an other replacement from that giant list again that allows me to replace each of those with these. Again, those are on the list. There's no explanation needed here. And I thought by starting with the right, it would give me sufficient algebra to have something to do. Look at the top problem that we're trying to prove. If I had started with 2 cosecant x, I'm not sure I would have had enough things to work with there to turn it into the right. Nonetheless, let's continue. I now decided to use a strategy called the common denominator strategy. It's basically turning 2 fractions into 1 by finding a common denominator. Now, you're already familiar with the concept. You maybe just haven't seen it in a trigonometric setting. But as a reminder from basic algebra, to get a common denominator, you have to get them to match by multiplying by 1. You may want to hit pause here and really analyze this and convince yourself that I chose a suitable 1 in each case to get a common denominator. So what I did next was I just noticed that I had 2 multiplications here. I'd just chosen to multiply by 1. I multiplied each pair of fractions straight across. On the first fraction, I didn't show my work, but I had to do FOIL to do 1 minus cosine times 1 minus cosine. The work's not shown, but the end result of FOIL is. Another thing that you might be wondering right now is why I didn't multiply the denominators. Each denominator is sine x times 1 minus cosine x. Why didn't I multiply that out and get sine x minus sine x cosine x? Well, again, you wouldn't know whether that's a good idea or not. And the first time I ever did this proof, I probably did multiply those out. Let's put that thought on the back burner and we'll come back to that. So now that I have a common denominator, I can merge my two fractions into one by simply adding the two numerators together, which I've done here, and keeping the same denominator. Well, the next thing that caught my eye, look at the numerator on the right side. I have cosine squared plus sine squared. There's a Pythagorean identity that allows me to change that into 1. Then what caught my eye is I can combine like terms in the numerator. 1 plus 1 is 2. At this point, I thought, maybe I could factor the numerator since there's a 2 in each term. So I factored the numerator, pulling out a 2 from that expression and leaving 1 minus cosine x, which was great news because now the 1 minus cosine x's are going to cancel. Now remember 3 lines up where I said, should I or shouldn't I multiply the sine x or distribute the sine x into the parentheses, 1 minus cosine? Sure, you could have, but you probably would have just ended up factoring it out later anyways. And in light of the fact that the 1 minus cosine x's cancel, leaving me just this, I'm kind of glad I didn't multiply the sine x through the parentheses. And now, since the sine is the reciprocal of the cosecant, I can use a reciprocal replacement and get 2 cosecant x, which is exactly what I wanted to get out of starting with the right side and working it out to be the left. Very tough proof here. This is probably one of the hardest ones I've ever seen. And that completes this video on proving trigonometric identities.